about what NASA is doing, having to do with things other than what's in this talk, but be advised that as a contractor, I can't really represent NASA, so I can just give you sort of my opinion about what's going on. What I'm here to talk about today is some work that we've done to try to determine when commercial clouds would be appropriate for use in NASA HPC. Let me give you some background of the supercomputing in the agency. The high-end computing capability project is the source of the money for the primary supercomputer center at NASA Ames. Basically, there's 900 users in the agency, 1,300 users in the agency who bring 900 applications to run on one of the 4 large machines that we have. Because this is the primary facility for the agency, we have a strong incentive to be as cost efficient as possible. The more science and engineering that we can do for the limited budget that we have, the better off NASA is for it. So we've done many things over the years trying to be cost efficient. One of the things that's sort of key for our effectiveness is a very high utilization rate of our system. We're embracing new technologies like the modular supercomputer center here. I'm happy to talk to you about that offline. And we're always evaluating procurement options. Well, you've maybe seen this picture. At least according to marketing reps, the cloud's the answer to everything, right? So I think these marketing reps got to NASA headquarters, and NASA headquarters turned around and asked HECC, so why aren't you using cloud? It's the answer to everything. So we undertook a study to determine when clouds would be appropriate for use in HECC. The questions that we wanted to answer were, would they be a cost-effective replacement for on-premises computing? And a secondary question, if they're not a cost-effective replacement, under what conditions could they be cost-effective? The approach we took was to compare the costs of running NASA workload on-premises and in the cloud. For on-premises systems, we used the Pleiades and Electra systems at NASA Ames. These are InfiniBand-connected Xeon-based nodes, several generations of which we have. And we compared those to Ethernet-connected Amazon Web Services resources, and then resources from Penguin On Demand that are connected with InfiniBand and OmniPath. The benchmarks we used, the NAS parallel benchmarks were used to NAS parallel benchmarks used to evaluate scaling and some general performance characteristics of the resources. And then we also use 6 full-size applications that we often use to represent the workload at NASA. 3 of them are from climate and weather modeling, and 2 of them from science. And normally when we're doing evaluations, we use 3 computational fluid dynamics codes. Well, because the computational fluid dynamics codes are export controlled, and the mechanisms that we were using for accessing cloud resources did not have moderate security plans with NASA, we couldn't use those codes. So we used OpenFOAM to substitute as the sort of CFD code that would represent the export controlled codes. Determining costs is actually one of the stickiest things that we had to do. So we decided to be in a sense, overly fair to the cloud providers. We didn't want to be subject to criticism for having put in a cost model that was unfair to the cloud and favored HECC in some way. So in fact, we used a pessimistic estimate of of HECC costs and an optimistic assessment of cloud costs. The HECC costs are actually they're actually the full cost of providing delivered resources to NASA users. We determine that full cost by looking at our budget and basically dividing by the number of billing units that we have delivered to users. We then can calculate the cost of a run as the number of billing units that were used in the run times the cost of each billing unit. Now, note that this includes all software, hardware, power, maintenance, and staff at the site. Is there a question there?
You're looking at the actual, just the run on a a VM or something, versus you don't include storage, software, bandwidth.
So what we're actually going to do is compare the compute-only costs on the cloud, ignoring all storage, bandwidth, everything else, and we're going to compare that to a full cost on premises.
But the data movement costs and the storage costs are often the things that will just completely crush you, right? In terms of just moving data, the network bandwidth.
Correct.
So how are you going to? I'm still not clear how you get sort of a TCO model that compares adequately.
This is a big problem. So
yeah.
So doing the analysis this way, we were able to establish that even being optimistic with respect to cloud costs and pessimistic with respect to HECC costs, we still don't. It's not cost effective to run in the cloud. So it's only going to get worse if we count the true costs of running in the cloud.
But if you think of it as not a cost issue anymore, you're optimizing across all if you're optimizing across all your workloads and you want to kind of onboard new customers into your user base, right? Then your costs are, you're looking at intangibles as well, which may obviate some of the true, like, sort of the financial issues, right? So I guess it depends on your strategy.
So I'm not
Meaning
sure.
that if part of the strategy is to grow your users and make sure your users have better turnaround time, and it's not if cost is not really what you're anchoring on.
I think we'll get into that
Okay,
in
thanks.
analysis. Let me know if we don't.
I have one question and one observation. The question is, what is the date of the benchmarking?
What is
the date?
The date was May.
May this year.
Yes.
Now, the second question is, in my opinion, it's a very good, just hands-off approach of evaluating the cloud for scientific applications, because if we want to have a very full, complete analysis of the cost, is not only the total cost of ownership of the data, but as well is the cost of opportunity or not having the latest hardware available, which you have in the cloud and not on premise. So there are many factors. That's correct. No, but this is good, but this is a very good approach, just for a quick and dirty see what is. Okay.
So this is a first approach, and I think one of the takeaways is that you can see there's a lot more refinement that's needed in order to come up with an accurate reflection of what the relative costs are. Okay, so in the case of the cloud, like I said, we used, in a way, a best case estimate. We looked at compute only. And in the case of Amazon, we anticipated what spot pricing would be. And the numbers that you'll see in this talk are assuming that we got spot pricing, which we calculated to be about 30% of the on-demand price. For Penguin On Demand, we use their published rates. Discounts are likely available, especially for volume. Actually, for this study, Penguin donated the resources, so in a sense it was free for us, but I don't think they'll do that in production. I should also say that Penguin is in the process of overhauling their rates, and I look forward to seeing what those are to repeat this analysis. So it should be noted that it is compute only. There's not costs for storage or licenses or bandwidth or staff or anything included in the cloud cost. So the rest of the approach is we're going to do a performance and cost analysis for jobs running on similar processor types, and then we're going to produce findings and identify actions for future work for HECC. So let's look at the kinds of resources that were involved. Basically, three generations of Xeons, Haswells, Broadwells, and Skylakes. You can see the relative costs. I've also provided sort of a crude extrapolation for comparison purposes, the numbers in blue, because it was often the case that, especially at Amazon, the parts that we were looking at, say the two Skylake parts, had different numbers of cores and wasn't really fair to do the comparison. If you just analyze this data, the first finding is that the per hour full cost of HECC resources is cheaper than the compute-only spot price at AWS and significantly cheaper than the price of similar resources at Pod. So let's look at some actual performance numbers then. Like I said, we started with NAS parallel benchmarks looking at scaling. We ran from 16 to 1024 MPI ranks. We found that the pod performance was similar to HECC. Not surprising because the resources were very similar. The interconnects were comparable, so we got the performance that we were expecting. The AWS performance was significantly worse, and especially worse on communication-intensive benchmarks. The graph is bt.c, block tridiagonal from the NAS parallel benchmarks. It's not particularly communication-intensive. It's actually pretty well balanced, as you can see from the blue communication lines in the graph. Look at the red communication line for AWS, and it's not very good. In fact, it becomes to dominate the whole cost of the run. And you see the turning point is at 64 ranks, which in the case of AWS, 64 fit on 2 nodes. So sort of within 2 nodes, you were okay. Once you went outside 2 nodes, trouble happened. If you looked at the full cost to run the set of the NPBs, Amazon was 6 to 12 times more expensive, depending on the processor type, and Penguin was 4.7 times more expensive. Let's look at applications. I think the takeaways here are that large computations took significantly more time again on AWS than on HECC. What we're looking at here is the AWS. We can look at basically times for the runs. We can see the performance ratio between AWS and HECC, and then the green line is the cost ratio. Keep in mind that, again, AWS was Ethernet connected. These applications have a communication requirement, and we weren't really achieving that on AWS. I'm sorry? You ran against spot instances, not reserved. Spot instances are known to not perform. I mean, it's not apples to apples, right? Why did you do a test against reserved instances?
So why spot instances and not reserved instances? I mean,
why spot?
Yeah, you basically said, give us anything you have left over, Amazon, and we'll put it up against our dedicated resources.
So again, spot is the most optimistic that we can do. Spot is going to be cheaper than reserved. So one of the things we're trying to establish here, I mean, we suspected this going in. If you have an existential threat to your organization that says you need to use cloud and you know that it's not the right answer, you do the analysis and show that no, cloud is not the way to go to replace all your on-premises computing. So you don't want to. I mean, if we make an assumption if we can stand by something that says we have been as generous as possible to the cloud case, and we still show that it is not cost effective, that's more effective than trying to come up with a very precise notion of cost.
I have an observation, because to me this thing is unfair. This comparison is very unfair. Because, for instance, AWS has no InfiniBand, and your applications require InfiniBand. And then the other thing is that there are other cloud providers that they have InfiniBand that are not here. And the business model for these cloud providers, depending on the list price, is not the best option, because the price depends on the amount of money that you commit. And then if you commit $1 million, I don't know. If you commit $20 million, it's different. For instance, we have moved everything to the cloud in my company, and we have discounts that are on the price list provided by everybody of 80%. 80%. So, for instance, we are running instances of 880 teraflops per minute. That in the past, the cost with on-premise computing was $100,000. Today, we do it for $200. You cannot even have a dinner with $200. So that means, I think that this is very interesting, but to be honest, this is not fully true, because there are things like, now you can, with the cloud, you can have the latest technology. You have everything that you don't have on-premise. When on-premise, you are stuck for several years with the same hardware, maybe 3 years least, while on the cloud, you have every job, you have the latest software, the latest hardware. In every job, different configuration of virtual machines. For instance, to store data in the cloud, depending on the cloud provider, is free. Why? They give you the cost of storage free because it's the way to hook you up. It's very bad, but it's the way it is. So they pay to have all the tracks to move your data from your center to their facilities, and they don't charge any money. But what happens? The catch is that if you want to move the data, then you have to pay. So, but this is what they do just to have you. But my point is that this is not.
So let's continue and let me get to the point that I want to make. So the Penguin performance, very similar to the HECC performance. Amazon at spot pricing, 1.9 times worse. If you were paying on-demand pricing, the full on-demand pricing would have been 6 times worse. The Penguin on demand, 5.3 times more expensive than running at HECC. The takeaway for NASA headquarters was that tightly coupled multi-node applications from the NASA workload take somewhat more time when run on cloud-based nodes connected with HPC level interconnects, but they take significantly more time on cloud-based systems using conventional Ethernet-based interconnects. So if we take those first 2 findings and combine them, we can get a cost-effectiveness finding that commercial clouds do not offer a viable cost-effective approach for replacing in-house HPC resources. I've mentioned this finding to people that I've met at different HPC centers, and they're astounded because they get very different answers when they do this sort of analysis. And so it's like, what's going on? Why do we find one thing and they find something else? So let's go through some of the possible reasons. Our applications may be different. The communication and computation patterns may be different. Our costs of providing resources are likely lower. I think that we actually are very cost effective when it comes to acquiring resources, when it comes to powering them and cooling them. The staff at our site is a good size for a large supercomputer center. And it's actually easy to add resources to our site without increasing staff costs. And that may or may not be true at smaller centers. They may have a larger percentage of their costs that are staff costs than we do. I think the number one point, though, is that we have really high utilization of our systems. We typically are running 80% or more utilized on our systems. The reasons for that, the system has evolved over time since 2008. It's effectively been the same system to the users over that time, starting with Intel Harper Towns and proceeding through all of the possible processor types through Skylake. And what that means is that there's not really substantial breaks for the user in their productivity. New resources come along, and they basically know how to use them. The environment that they're running in stays the same. We also minimize the downtime for maintenance. This is NASA's primary supercomputer facility. We don't take weekly maintenance to address system concerns. We try to do those things in an ongoing fashion, and in fact have developed technology to allow us to do that. So given all this, are there things that HECC could do to use cloud and still be cost effective? Yes. I mean, if the utilization of some system would be low, it probably makes sense to move that into the cloud. Also, the cost model that we're talking about is only talking about monetary costs that are directly measurable. There's other costs that we should consider, namely opportunity costs. One of the costs of having high utilization is that there's long queue wait times. And our users are used to that. I mean, it's common for somebody that's asking for 500 nodes to run for 5 days to have to wait for 5 days for those resources. So there's a cost to them to do that, though. How you monetize that cost, I'm not sure, but that's something that we need to worry about. If we had real-time requirements, say, to provide web services where there was a highly variable demand, that work might be good to put off in the cloud as well. So the fourth finding is commercial clouds can provide a variety of resources that we don't have, and certain use cases may be effective to run there. We identified some follow-up work. I'm going to sort of go through this quickly in the interest of time. We need to understand things like, in understanding the opportunity cost, it was suggested that maybe we should take all the one-node jobs on the system and move them off to the cloud, and that would speed up the scheduling of larger jobs. Also in this follow-up work, I think it's clear that we need to have a better cost model than we do. Because if we're actually going to be making decisions for procurement based on cost as a primary factor, we need to really understand how to get a handle on costs that are comparing apples to apples. And finally, we anticipate that cloud is part of the future for HPC at NASA. And so we're gonna implement, basically for now, cloud bursting from our system to AWS. And we are targeting both our current users and other users in the agency who aren't currently users of our system, but nonetheless have high-performance computing requirements. These are probably people running departmental level servers now. So it turns out, if you look at the scheduling impact of running one-node jobs in the cloud, it doesn't really help schedule the larger nodes very much faster. Our tests with real data show that they would speed up an average of 2 hours of queue wait time by removing all the one-node jobs. Like I said, we have started a pilot project to do cloud bursting. We've also done a lot of work on containers. And for the future, what we want to do is extend that pilot with the cloud bursting, adding accounting and a moderate security plan. We also want to extend the services to users in the agency who aren't currently using the supercomputers. In this case, they'll bring their own funding. And finally, we need to do a lot more work on how we compare costs, as we've talked about. This is the team that did the work, and at the bottom is the technical report that you can access online with the results of the study. That is the talk.
Just speaking as a bit of a voice from the future on this, having done similar analysis about 4 years ago, I think you're targeting many of the right things. And the comments that Francisco made, it's actually where we ended up as well. For the core of our HPC service focused on thermosciences, grid space resolution, large-scale CFD, the cloud just will never make sense. Maybe in the future, but not anything we've seen so far, for one very simple reason. Your costs and my costs and the cloud provider's costs on the hardware are all asymptotically approaching the same number. They have marketing costs, sales costs, et cetera. It's just a difference. But for what you're talking about, where we can find classes of workloads that are highly accelerated for the cloud, that's incredibly valuable to the business. So what we did in GE is we offer both an HPC service, and to the point you're making, the ability to extensively stretch workloads out to multiple vendors. We can talk more offline about it, but it really accelerated things like cycle deck runs and those kinds of things for us.
I'm going to throw one more comment in. So, and by the way, you have a lot of the right metrics, and it's spawning all the fun discussion here today, so thank you. It's really a great baseline deck for everybody here to take a look at. You should be looking at this.
So this morning wasn't a good indication of how much interaction there was.
Yeah, this is really an excellent piece of work here, and really we're just offering some commentary because we have an elastic hybrid cloud environment that we've been operating for a while now in production, and we really use it every day. One area where I think we can just help by saying to the audience here that you need to take a look at is the middle ground jobs, because what you haven't necessarily put into this is kind of like your throughput and size of jobs. And I'm just saying that really generically, size of what type of capacity you're looking for, but it's those middle ground jobs. Maybe at NASA, you have access at your fingertips to find that compute capacity. But for industry, those middle to larger scale jobs where it exceeds our internal capacity and capabilities, and we're not always able to just get capacity somewhere else on a national lab environment, an elastic hybrid cloud makes a lot of sense because you can spool up whatever volume of nodes you want for a very predetermined specific amount of time, and you only may need to do that 3, 4, or 5 times. And if you look at the cost impact of that for how fast you're able to do that needed capacity, it makes a lot of sense from a total cost of ownership standpoint.
In our environment, if there's a requirement that requires elasticity of some sort, it's often handled by adjusting shares across the different missions and say, human exploration has a need over the next 3 weeks for some really intensive
But industry in general doesn't have that.
Correct. So again, this is NASA is probably a special case here. So, and I want to be completely upfront with that. Our demand is very high. When we add resources, they're almost immediately subscribed to. So we have a lot of unmet demand. And if we need to add resources, which we do, it's probably cheapest for us to go out and buy them. And then the costs that I've represented here are even lower because the marginal cost of us adding a resource is probably half of the true costs, the average costs that I was representing here.
This is a great overall study for many people. So, because in most other cases in industry, this study is not necessarily on public display.
So just to corroborate the data point, Compute Canada did a very similar calculation when they purchased a 6,000 core OpenStack system about 2 years ago. The factor comparing against Amazon was about 5 to 1. In other words, the Amazon cost comparable compute capability was 5 to 1 more expensive. A couple of factors on that. One is configuration issues. Aside from connectivity, InfiniBand, et cetera, which is increasing. You see in Amazon providing greater and greater InfiniBand network sizes. But other things are presence of a high-performance file system, not available in Amazon, at least to my knowledge, and also what is the onboard memory configuration or onboard storage configuration, often not comparable to what you would see in a system you would build on premises. So these are factors that also should be flowed into the analysis going forward. What are those architectural requirements?